Okay, so I want to start looking at rational functions. And if you notice our calendar, rational functions is a very large topic. And so we're going to divide this up and really break this down. But our goal, so do you know from the very start, our goal is to be able to analyze rational functions without the use of a calculator. So that's sort of our goal. So there are a few terms and things and features we want to talk about. First of all, what's the definition of an asymptote? Okay, so an asymptote. Okay, so the definition of an asymptote predicts the behavior of a function or a graph. Most of these, since we're dealing with rational functions, I'll say functions, that's fine. Asymptotes predict the behavior of a function, okay, or a graph. Because the asymptote itself is not part of the function. So you'll see them on a graph because all of a sudden your graph will start behaving a certain way. It might start appearing to go straight up, like along a vertical asymptote. That asymptote predicts that behavior. Okay, so I should say, note, it's not part of the graph. And maybe in other classes, maybe they talked about it as like almost like a boundary. And the thing about a boundary, though, is that I'm putting it in quotes because boundaries kind of, to me, tell me that I can't touch that, like it's out of bounds, right? But there are some asymptotes you actually can touch. So that's going to be maybe a different thing this class. There are several kinds of asymptotes. There's vertical, and you definitely cannot cross or touch a vertical asymptote. There's horizontal, which, depending on the function, you actually can cross a horizontal, and we'll see some of those. And then there's oblique. And oblique, I think, vertical, we know what that looks like. Horizontal, we know what that looks like. And so the word oblique just means it goes at an angle. So it's not vertical or horizontal, yet it's still linear. Okay, so those are the three kinds of asymptotes. And I should say that those are linear because there are other asymptotic behaviors that we could analyze, like quadratic asymptotes, things that start behaving like a quadratic function or cubic or other things. So again, the definition of an asymptote is this predicting the behavior. Okay, and it's not part of the graph. It's sort of like a boundary, but you might be able to touch that. And again, maybe I'll even mark that on my notes here. You can sometimes cross this one, and you can sometimes cross this one. Again, it depends on the function. Okay, now a hole is just a single point of discontinuity. Okay, it's a single point of discontinuity. And it arises from having both a zero in the denominator, because you can't divide by zero, but also in the numerator of this rational function. It's a result of a zero divided by zero. And it's kind of funny because I talk about this in class all the time, but 0 over 0 is like one of the most important numbers in calculus. And it's called an indeterminate form of a number. And indeterminate because you can't determine what is actually happening, what is the behavior, what is the function really looking like or doing, because that 0 over 0 is sort of masking what's happening. Okay, now we're going to look at a difference between a vertical asymptote versus a hole. And I'm going to kind of slide this way and slide this way, because 0 over 0 is indication of a hole, right? So 0 over 0, we know that we should be looking for a hole, this single point of discontinuity, right? So again, you might have a graph and there might be just like one gap and then it continues, like this one point of discontinuity. And in calculus, we call it a removable point of discontinuity. Okay, now, if you have any other number divide by 0, then you know that you have a vertical asymptote. And so that's one of the first things that we're going to have to be able to distinguish and recognize is if you have a rational function, right? It's like basically a polynomial both in the numerator and the denominator. How do you distinguish? Does it have a whole or a vertical asymptote? So, all of these examples are rational functions. They all are fractions, or fractional functions. And so, if I look here for A, I notice that there's a 0 in the denominator when x is 1. So I really don't want to let x equal 1. But there's no other time where like when x is 1, like the top doesn't become like a 0 over 0. So the fact that like when x is 1, I get 2 over 0, like that puts me in the category there's a vertical asymptote. So there's a vertical asymptote at x equals 1. And that's the equation of a vertical line. So like I would know that at x equals 1, right, there would be a vertical asymptote that I could label 1. Now you can never cross a vertical asymptote, and this would indicate the behavior, the graph might be trending up, like straight up. It might be trending down. It depends on, again, the nature of the function. Okay, now, so looking at this next example, I noticed that I can't choose 7, like x can't be 7 because I can't divide by 0. Now, like when I choose x to be 7, like that's the only time there's a 0 in the bottom. And when I choose that 7 plus 5 over 0 or 12 over 0, again, that's an indication we have a vertical asymptote. We'll call it VA because it's that's kind of a longer word to spell, asymptote. So I know there's a vertical asymptote. So I know that the equation of that vertical asymptote is x equals 7 because that's the equation of a vertical line. Okay. So again, if it's any other number, again, focusing like the first time was 2 over 0. This one was 12 over 0. If it's any number over 0, other than 0 over 0, you have a vertical asymptote. Okay. Now, the next example, I noticed that I can factor the numerator. So if you factor the numerator first to see that that's x minus 1 times x minus 3 over x minus 1. Okay, so like the fact that we can actually cross out this factor here, like this factor here and this factor here, when you can remove that and you can remove the 0 in the denominator, that's an indication you had a whole. Because like right away, like I know that x can't be 1 because that would have provided a 0 in the denominator. But if you try to put 1 up here, you'd get 1 minus 4 plus 3. You get another 0 over 0. So when you have 0 over 0, that's an indication that you have a whole. So there's this removable point of discontinuity. And again, if I'm looking at my factors, like right here, like x is minus 1, x minus 1, notice when you choose like x to be 1, that is your 0 over 0. So we're removing that 0 over 0, and we're reducing it down to x minus 3. So we're getting an equivalent expression for every other point other than that one instant we removed. So we have an expression that's been what we call reduced. So this is a reduced function. And what you can do to obtain the whole is, since we crossed this out, this x minus 1, cross it out, we know that 1 was the issue. So since that was x equals 1, I know the coordinate of that whole will be 1. And what you can do is you can take that 1 and input it into the reduced function. So then I could say, okay, so now my reduced function is x minus 3. So then if I input 1 and then subtract 3, the reduced function would give me negative 2 as the coordinate. So when your function as a whole, it's going to have an x and a y. The x will come from what you crossed out. So since I crossed out a factor that would have been like if x were 1, it would have been undefined. So that determines the x component. And then how do you get this y value? You actually you put that x value into the reduced form. And that's what I did to get negative 2. Okay, so we're gonna do the next ones on the next video, but I just wanted to at least give you some heads up here on this particular, this particular set of examples.